In this screencast, we're going to revisit the center of mass, and we're also going to add an idea called the radius of gyration, which you can think of as a rotational center of mass. First, the idea. Suppose you're standing on a pier, and you've got one person who weighs 50 kilograms standing 1 meter out, and another person who weighs 100 kilograms standing 4 meters out. The idea, the question is, if I just take these two people, one weighing 50, one weighing 100 kilograms, and I just look at them alone, how can I find their center of mass? And the idea is, if these two people were to walk and stand at one specific spot, where should they stand so that they generate, in some sense, the same distance, or the same weighted distance to the origin? So the idea, this distance is 1 meter. So I've got somebody 1 meter out who weighs 50 kilograms. You can think of it as an x distance times a little bit of mass. This person is 4 units out, and they weigh 100 kilograms. So I can think of that as an x distance times a little bit of mass. If I add these up, which would be like adding up the x's times little bits of mass, well, then over here I get 50 plus 400, which is 450 meter kilograms. Well, over here I had to get something else. The question I want to ask is it possible to take all of the weight, there's 100 here and 150 here, can I take the two, have them stand in the same spot, and get the exact same average mass? Well, 450 divided by 150 is 3, which means if I make both people stand at this spot, then this number would be the same if I put a 3 in there. So I could think of this as x bar times add up the masses. The center of mass is precisely where should everyone stand so that this weighted distance to the origin is the same. Another way you can look at it is if you think of it as a teeter-totter, and you just look at this person sitting on one end of a teeter-totter and that person sitting on the other. If you put the balancing point right there, then this distance of 2 meters times 50 kilograms would be 100, whereas this distance of 1 meter times 100 would be 100 kilograms, and you'd have the same weighted distance on both sides. The idea, the key idea I want us to focus on is that if you add up the varying x's with respect to mass, and I'm going to put that x bar inside, where should you take the varying x distances and place all of them at the same spot? So take everything, put it in one spot, so that these two sums are the same. This is often called a first moment of mass. But the word moment means many different things in different places, so we're going to avoid using that too often. But the idea is, where can I place all the mass at one specific spot so that these two integrals are the same? And once you've done that, you can pull the x bar out. And then if you want to solve for x bar, it's just this quantity, x dm, over that quantity, integrate dm. It's add up all the x values times their masses and divide by the mass. That is how you find center of mass. Now we're going to hit the idea of radius of gyration, or radii of gyration. It's very, very similar. The idea is when you're rotating something, if you're going to take an object and you're going to rotate it about an axis, then that object rotates a certain inertia. Inertia is you add up the radii squared dm. But these radii are varying just like these x values were varying. So if you take those radii and say, let's take all the radii and put them at one single spot, we'll put it at a big R, then where should this single spot be? What should the single radius be so that the entire inertia stays the same? Well, that's a constant, so we'll pull it out. And then I'm adding up little bits of mass. Well, this is just a mass. So I really have the equation I equals r squared m. I can solve for r, which is just I divided by m, and then take a square root. This is called a radius of gyration. I'd like to just show you a visualization of what that could be, and then we're going to work through the example. If you take a helix which wraps around a cylinder, and you started rotating it about the z-axis, then the radius would be the distance out. You essentially could take the entire helix and put it on a cylinder. It already is on a cylinder, and so there's no need to change the radius in that case. But if I take this helix and I rotate it about the x or the we can go about the x-axis or the y-axis. Then what that does is it gives me a radius of gyration. That would be the radii of these circles. And those radii tell me precisely where should I push the entire arc out to so that I end up with the exact same moment of inertia. So we're going to look at an example. We're going to take the helix. We'll go with cosine t, sine t. We already know in all these problems we need a derivative, so I'm just going to take it right now. We get a negative sine t, cosine t, 1, and I need a speed. Sine squared plus cosine squared is 1 plus 1 squared. So that's just root 2, which means my ds is root 2 dt. If I want to get a dm, I need a density. Densities are going to be given to you in the problem. In this case, let's just assume it's constant and it's 3. So the mass is density times ds, which in this case will just have to be a 3, and the ds is our root 2 dt. So anywhere I see a dm, I'll put in this quantity. Which means up here, if I'm trying to do an inertia, if I'm trying to do a radius of gyration, I need an inertia. Well, if I want to do the radius of gyration about the y-axis, it would mean let's find the inertia about the y-axis and divide by the mass. How do I get the inertia about the y-axis? Well, I need the radius to the y-axis. Square it, and then add up little bits of mass. How do you get the radius to the y-axis? Well, if I take a point in space, and I want the distance from that point down to the y-axis, then I need to know an x value, and I need to know a z value, and this distance up here is the square root of x squared plus z squared. So, if I want to take that radius and square it, it's just x squared plus z squared, where you square the square root. And that is my inertia about the y-axis. Well, I know the x value is my cosine. So that's a cosine squared. I need to know my next value, the z value, which is a t. And then I need to multiply that by dm, which is 3 root 2 dt. That's my inertia about the y. I do need bounds. If I want to go around the helix once, then the bounds are going to go from 0 to 2 pi. So we'll put a 0 to 2 pi in. To get the mass, I add up little bits of mass, which we already got. We just need a 0 to 2 pi. My little bits of mass are 3 root 2 dt. So if I want my radius of gyration about the y-axis, it should be the square root of that quantity, I sub y, over that quantity, which is my m. And that's my radius of gyration about the y-axis. This picture here essentially shows me the visualization that the radius of gyration about the y-axis tells me that distance. That completes the screencast.